somewhere in the dry, sun-scorched lowveld of southern Africa, a rock hyrax sits at the edge of a granite outcrop, basking in the late morning warmth. The little mammal is plump and still, its round body soaking in the heat of a cloudless sky. It does not notice the long, dark shape sliding through the scrub below. The movement is nearly imperceptible, a ribbon of gunmetal gray flowing over red earth and dry leaves, with a silence that borders on supernatural. Then, in a heartbeat, the shape rises. A full third of its body lifts straight off the ground, more than 3 feet of muscular neck, and coffin-shaped head ascending like a periscope above the grass. For a fraction of a second, there is stillness. Then the mouth opens, revealing a void so dark it seems to swallow the light itself. The hyrax never stands a chance. 2 strikes land in under a second. The fangs sink, pump, and withdraw. The snake releases its prey and glides backward, watchful, patient. The hyrax stumbles a few steps, wobbles, and collapses. Within minutes, the neurotoxins flooding its bloodstream shut down the signals between its brain and its lungs. Breathing stops. The heart follows shortly after. The black mamba, unhurried now, slides forward to claim its meal. This is what makes the black mamba the single most feared snake on the African continent, not merely the venom, though the venom is extraordinary. Not merely the speed, though the speed is staggering. It is the combination. It is the totality of the animal, a creature that brings together length, agility, intelligence, and one of the most sophisticated chemical arsenals in the natural world into a single, sleek, terrifyingly efficient package. Let that opening scene settle for a moment, because here is a fact that might keep you watching. A single bite from an adult black mamba can deliver enough venom to kill somewhere between 10 and 15 grown adults. 10 milligrams of that venom is considered a lethal dose for a human being. The average bite delivers between 100 and 120 milligrams. Some large adults have been recorded delivering 400 milligrams in a single bite sequence. That is 40 times the lethal dose, injected in a matter of seconds, from a snake that can strike repeatedly in the blink of an eye. Before the development of a specific antivenom in 1962, the fatality rate from a confirmed black mamba envenomation was, by all credible accounts, 100%. Every single person who was bitten by a black mamba and received a full dose of venom died. Everyone. And yet, despite that reputation, despite the mythology that has grown up around it across dozens of African cultures, the black mamba is not the mindless killing machine most people imagine. This is a creature of nuance, a creature of contradictions. It is shy, but capable of extraordinary aggression when cornered. It is solitary, but engages in one of the most dramatic mating rituals in the reptile kingdom. It carries death in its fangs, but also harbors molecules that could one day replace morphine as the world's most powerful painkiller. The black mamba is, in every sense, one of the most remarkable animals walking, or rather slithering, across the surface of this planet. Tonight, we are going to spend some time in its world. We are going to trace the evolutionary path that produced this extraordinary predator, explore the savannas and rocky outcrops it calls home, Dissect the biochemistry of its venom molecule by molecule. Watch it hunt, fight, mate, and raise its young. And confront the uncomfortable question of what happens when its world and ours collide. By the end of this, you may not love the black mamba, but you will understand it. And understanding, more often than not, is the first step towards something better than fear. So settle in, dim the lights, and let us begin with the most basic and most commonly misunderstood fact about this animal. The black mamba is not black. The scientific name of the black mamba is Dendrospes polylepes, and every piece of that name tells a story. Dendrospes comes from the ancient Greek words for tree and shield or asp, a reference to the climbing ability shared by all members of the Mamba genus. Polylepes translates roughly to many-scaled, a nod to the unusually high number of dorsal scales running along the snake's body, typically between 23 and 25 rows at mid-body, with 248 to 281 ventral scales along the belly, and over 100 divided subcaudal scales beneath the tail. The word mamba itself comes from the Zulu language, derived from a mamba, the traditional name given to several large, venomous snakes in the region. In Tanzania, among the Ngindo people, the black mamba goes by the name Endomalinieo, which translates colorfully and somewhat ominously as grass cutter, a reference to the local belief that the snake clips the grass as it moves through the bush at speed. The black in its common name has nothing to do with the color of its skin. From a distance, a black mamba looks almost nothing like what most people expect. Its body is typically olive, gray-brown, khaki, or gunmetal in color, occasionally with a subtle purplish sheen to the scales. Some individuals display dark diagonal mottling or crossbend patterns toward the tail, but the overall impression is of a long, sleek, somewhat understated snake. The underbelly is soft, grayish-white. Juvenile mambas are even lighter, usually pale gray or olive green, darkening gradually as they mature. You could walk past a young black mamba in the bush and mistake it for any number of harmless species. The black refers instead to the inside of the mouth. When a black mamba feels threatened, when it rears up and opens its jaws in that famous threat display, the first thing you see is a cavity so deeply pigmented that it appears almost violet black, a dark bluish gray that can verge on true ink black depending on the individual and the light. That gaping void of color against the lighter scales of the body is one of the most striking warning signals in the animal kingdom. It is designed to shock, to stop a potential predator in its tracks. And by all accounts, it works. The body itself is built for speed and reach. An adult black mamba typically measures somewhere between 6.5 and 10 feet in length. That is the average range. But this is a snake that can grow considerably larger than average. Specimens of 14 feet and beyond have been reliably documented. The current record holder, measured in Zimbabwe, stretched to approximately 14.5 feet. At that length, a black mamba is taller than almost any room you have ever stood in if you could somehow stand the snake on its tail. Not that you would want to. Despite that impressive length, the black mamba is not a heavy snake. The body is slender and cylindrical, almost elegant, tapering to a long, whip-like tail that makes up roughly 17 to 25% of its total length. An average adult weighs somewhere around 3.5 pounds, though a large specimen can push past 5 pounds. The head is distinctive, often described as coffin-shaped, with a slightly pronounced brow ridge that gives the snake a perpetually stern, focused expression. The eyes are medium-sized, ranging from grayish-brown to deep black, and surrounded by a thin ring of silvery white or pale yellow. Those eyes are not just decorative. Black mambas have excellent vision, particularly for detecting movement, and they rely on their eyesight during the hunt far more than most snakes do. Then there are the fangs. The black mamba is protroglyphous, a term that means front-fanged. Unlike vipers, which have long, hinged fangs that fold against the roof of the mouth, the mamba's fangs are relatively short, fixed in position at the front of the upper jaw, and permanently erect. They measure up to about 1/4 inch in length, roughly 6.5 millimeters. That might not sound like much, but those fangs do not need to be long. They are hypodermic needles, precision instruments designed to puncture skin and deliver venom directly into the tissue beneath, and the mamba can use them with devastating speed and accuracy. The black mamba was first formally described by science in 1864 by Albert Gunther, a German-born British zoologist working at the Natural History Museum in London. The specimen he described had been collected by John Kirk, a physician and naturalist who accompanied the famous explorer David Livingstone on the second Zambezi expedition between 1858 and 1864. That original specimen, the holotype, is still housed in the Natural History Museum today. A few years later, in 1873, German naturalist Wilhelm Peters described what he believed was a separate species from a specimen collected in what is now northern Eritrea. That species was eventually reclassified as a subspecies, and today it is no longer considered distinct. In 1896, the Belgian-British zoologist George Boulanger merged the black mamba with the eastern green mamba into a single species, a classification that stood until the South African herpetologist Vivian Fitzsimons separated them again in 1946. A genetic analysis published in 2016 confirmed that the black mamba and the eastern green mamba are indeed each other's closest living relatives, both members of the genus Dendrospes, but clearly distinct species with very different ecologies and behaviors, which brings us to the wider family tree. The black mamba belongs to the family Elapidae, one of the most formidable groups of snakes on the planet. The elapids include cobras, krites, coral snakes, taipans, and sea snakes, an all-star lineup of venomous species that together account for a staggering proportion of the world's snakebite fatalities. What unites all elapids is that front fang arrangement we just discussed, along with venom that is predominantly neurotoxic, targeting the nervous system rather than the blood or tissue. Within that family, the genus Dendrospes contains 4 recognized species. 3 of them, the eastern green mamba, the western green mamba, and Jameson's mamba, are primarily arboreal, spending most of their lives in trees and all three are bright green. The black mamba is the outlier. It is the only member of the genus that is predominantly terrestrial, the only one that regularly hunts and lives on the ground, and the only one that is not green. That ecological distinction, as we will see, has had a profound effect on everything from its venom chemistry to its behavior. To understand where the black mamba came from, you have to go back a very long time, long before the savannas of modern Africa existed in their current form, long before the genus Dendrospes split into the 4 species we know today, back to a period when the ancestors of all snakes were just beginning to experiment with a radical new body plan. The story of snakes begins in the Cretaceous period, somewhere between 150 and 100 million years ago, when a group of lizard-like reptiles began to lose their limbs. The reasons for this are still debated among paleontologists, but the prevailing theory is that these early proto-snakes were burrowers. They were small, elongated creatures that lived underground or in dense leaf litter. And over millions of years, natural selection favored a body plan that was increasingly streamlined. Legs became smaller and eventually vanished entirely. The skull became more flexible, and the jaw unhinged to allow for the swallowing of prey larger than the head. The body stretched out, vertebrae multiplied, and muscles adapted to generate movement through undulation rather than walking. The earliest known snake fossils, creatures like Najash rheumgrina from what is now Argentina and Coniophas procedens from North America, date to the middle of the Cretaceous, roughly 90 to 100 million years ago. These were small, unassuming animals, nothing like the apex predators that would eventually descend from them. The ancestor of all modern crowned snakes, the group that includes every living snake species, likely appeared during the late Cretaceous, perhaps 80 to 90 million years ago. Research published in the journal BMC Evolutionary Biology suggests that this ancestor was a nocturnal, ground-dwelling predator that inhabited warm, moist, forested environments on the ancient supercontinent of Gondwana. It was a carnivore, probably feeding on small reptiles and amphibians, and it would have been completely unrecognizable as the ancestor of something like the black mamba. The real diversification of snakes came after the mass extinction event that wiped out the non-avian dinosaurs 66 million years ago. With so many ecological niches suddenly vacant, snakes underwent a dramatic evolutionary radiation. New families appeared. New feeding strategies emerged. Venom, which had likely existed in rudimentary form in some earlier lineages, became increasingly sophisticated and diverse. By the Eocene epoch, roughly 56 to 34 million years ago, the major snake families we recognize today were beginning to take shape. The family Elapidae, to which mambas belong, is thought to have originated sometime during the late Eocene or early Oligocene, roughly 30 to 35 million years ago. The question of where the elapids first evolved has been the subject of considerable scientific debate. For many years, the prevailing view held that elapids originated in Africa and then dispersed outward to Asia, Australia, and the Americas. But a study published in 2024 in the journal Royal Society open science challenged that narrative. By analyzing the DNA of 65 snake species and incorporating genetic data from over 400 additional species, a team of evolutionary biologists built a comprehensive elapid family tree. Their analysis pointed to Asia, not Africa, as the most likely origin point for the elapid lineage. Two early diverging groups, the cyclochorids and mock vipers, both split off while living in Asia, suggesting that the common ancestor of all elapids was also Asian. From Asia, the elapids appear to have dispersed widely. Some lineages moved into Australia, where they underwent a spectacular radiation that produced taipans, tiger snakes, death adders, and sea snakes. Others moved into the Americas, giving rise to coral snakes. And at some point, perhaps during the late Oligocene or early Miocene, roughly 20 to 25 million years ago, at least one elapid lineage made the journey into Africa. This lineage would eventually give rise to the African cobras, the rinkholes, and, crucially, the mambas. The earliest definite elapid fossils in Africa are scarce. Snake fossils in general are rare because the skeleton of a snake, with its hundreds of small, delicate vertebrae, does not preserve well. But a fossil fang discovered in the Bolt's Farm Cave system in South Africa's cradle of humankind, dating to the Pleistocene, roughly 2 to 3 million years ago, has been identified as belonging to a spitting elapid, confirming that the family was well established on the continent. By that time, the Mamba lineage itself is thought to have diverged from its nearest relatives, probably a cobra-like ancestor, sometime during the Miocene, roughly 10 to 20 million years ago. Genetic evidence suggests that the genus Dendrospes then split into the 4 species we know today over the course of several million years, with the black mamba and the eastern green mamba being the most recent to diverge from each other. What is particularly fascinating about the black mamba's evolutionary path is how it departed from the lifestyle of its closest relatives. The other 3 mamba species are all arboreal, living primarily in the canopy of tropical and subtropical forests. The black mamba, by contrast, moved to the ground. This shift from tree to earth had cascading consequences. On the ground, the snake encountered different prey, primarily small mammals, rather than birds and lizards. It faced different predators, and it needed to move differently, faster, and farther across open terrain to survive. These pressures drove the evolution of the black mamba's most distinctive traits: its exceptional speed, its larger body size, and most importantly, its uniquely specialized venom. The composition of black mamba venom differs markedly from that of the green mambas, and researchers believe this divergence reflects the dietary shift that came with its ground-dwelling lifestyle. Small mammals, with their warm blood and fast metabolisms, require different toxins to subdue than the cold-blooded prey that dominates the diet of arboreal species. In a very real sense, the black mamba we see today is the product of a long and winding evolutionary journey, from limbless burrowers in the age of dinosaurs to early elapids in the forests of ancient Asia, to the unique ground-hunting apex predator of the African savanna. every adaptation it carries, its speed, its venom, its size, its coffin-shaped head and ink-black mouth, is a chapter in a story that stretches back tens of millions of years. The black mamba is a creature of sub-Saharan Africa, and its range is enormous, from the rocky highlands of Eritrea and Ethiopia in the northeast, down through Kenya, Uganda, and Tanzania in East Africa, across the woodlands of Mozambique, Malawi, and Zambia, into the savannas of Zimbabwe, Botswana, and Namibia, and south into the provinces of South Africa and the small kingdom of Eswatini. This snake occupies a vast swathe of the continent. Its distribution also extends into parts of Central Africa, including the Central African Republic, the Democratic Republic of the Congo, and Burundi, though it becomes patchier in the more densely forested regions of the West. There have been scattered reports from West African countries like Cameroon and Burkina Faso, and even a couple of unconfirmed sightings from Senegal in the 1950s. But the black mamba is fundamentally an Eastern and Southern African species. Within that range, the black mamba shows a clear preference for moderately dry environments. It is not a creature of the deep, humid rainforest, nor of the open, treeless desert. It thrives in the transition zones, the places where scattered trees and scrubby vegetation meet open ground. Light woodland, rocky outcrops, semi-arid savanna, moist savanna, and the edges of lowland forests are all classic black mamba habitats. The snake particularly favors areas with good basking sites, spots where it can soak up the morning and afternoon sun, as well as ready access to shelter. Termite mounds, abandoned animal burrows, rock crevices, hollow trees, and fallen logs all serve as refuges. A black mamba will often establish a permanent lair in one of these structures and return to it day after day, sometimes for months or even years, provided it is not disturbed. In South Africa, the black mamba is increasingly being encountered in suburban and even urban areas, particularly around the city of Durban and the broader KwaZulu-Natal province. This is not because the snakes are seeking out human company. It is because human settlement is expanding into areas that were once bush and scrubland, precisely the kind of habitat the mamba prefers. As vegetation is cut back and houses are built, the snakes find themselves living in uncomfortably close proximity to people. They are drawn to human structures in part because those structures often attract the rodents and other small animals that make up their diet. A roof space or a garden shed, from a mamba's perspective, is just another kind of shelter, and one that happens to be conveniently close to a reliable food source. The snake is not commonly found at high altitudes, generally preferring to stay below about 3,300 feet above sea level. However, there are exceptions. In Kenya, black mambas have been recorded at nearly 6,000 feet, and in Zambia, they have been found at over 5,400 feet. These are outliers, though. The typical black mamba is a lowland animal, a creature of warm, sun-drenched landscapes where the temperature stays high enough to support its cold-blooded metabolism for most of the year. Unlike the other mamba species, which spend the majority of their time in the canopy, the black mamba is primarily terrestrial. It moves along the ground with its head and the front portion of its body raised, a posture that gives it an excellent vantage point for spotting both prey and threats. But it is not exclusively a ground dweller. Black mambas are surprisingly capable climbers, and they will ascend into trees and bushes to bask, to hunt, or to escape danger. They have been observed moving through the canopy with remarkable agility. And during the mating season, rival males have been filmed wrestling in the treetops. The snake's long, muscular body and gripping belly scales give it a secure hold on branches, and its speed does not diminish much when it goes vertical. One of the more interesting aspects of the black mamba's habitat use is its relationship with termite mounds. Across much of its range, particularly in the drier savanna regions of southern Africa, termite mounds serve as ready-made fortresses for mambas. These structures offer thick, insulating walls, protection from the elements, and a labyrinth of internal chambers and tunnels that are nearly impossible for most predators to penetrate. A mamba that takes up residence in a large termite mound has access to a climate-controlled shelter that stays cool during the heat of the day and retains warmth through the cool nights. It is not uncommon for a single termite mound to be used by the same individual mamba for months or even years, becoming a well-established home base from which the snake ventures out to bask and hunt before returning each evening. Black mambas are diurnal, meaning they are active during the day. In South Africa, they have been recorded basking between roughly 7 and 10 in the morning, and again in the early to mid-afternoon, between about 2 and 4. Between those basking sessions, they may hunt, patrol their home range, or simply rest in the shade of their lair. As dusk approaches, they retreat to shelter for the night. They are solitary animals outside of the mating season. Black mambas do not seek out the company of other mambas and will generally avoid each other. Each individual maintains a home range, the size of which varies depending on the density of prey and the availability of suitable shelter. They are not considered highly territorial in the way that some mammals are, but they do show strong site fidelity, returning to the same basking spots and lairs with remarkable consistency. The speed of the black mamba is the stuff of legend, and like most legends, the truth has been stretched a little over the years. You will sometimes hear claims that the black mamba can outrun a horse or chase down a car. These are exaggerations, but the reality is impressive enough that it does not need embellishment. The black mamba holds the Guinness World Record as the fastest land snake on the planet. In controlled measurements, it has been clocked at speeds of up to 12.5 miles per hour over level ground. Some sources cite slightly higher figures, up to about 15 kilometers per hour, or just over 9 miles per hour as a sustained speed, with the 12.5 mile per hour figure representing short, explosive bursts. To put that in perspective, the average human jogs at about 6 miles per hour, meaning most people, if they were not already running at full sprint, would not be able to outpace this snake. An Olympic sprinter could leave a black mamba in the dust, but your average person on a trail in the African bush would be in real trouble. The snake achieves this speed through a form of locomotion called lateral undulation, essentially an S-shaped motion in which the body pushes off against irregularities in the terrain, rocks, roots, ridges of compacted soil, to generate forward thrust. Its smooth, low-friction scales and long, muscular body are perfectly adapted for this style of movement. On flat, open ground, the mamba flows across the surface with an almost liquid grace, its body forming a series of rapid, shallow curves that propel it forward with remarkable efficiency. When moving at speed, the black mamba raises the front third of its body off the ground, a behavior that reduces drag and gives the snake a better field of vision as it moves. But raw speed, as impressive as it is only part of the story. What makes the black mamba truly formidable as a predator is the combination of that speed with its striking ability. When a mamba strikes, it does not lunge forward in a single slow arc like many other snakes. It fires. The head accelerates with explosive force, driven by the same powerful muscles that propel the body across the ground. A black mamba can deliver multiple strikes in rapid succession, biting, withdrawing, and biting again in the space of a second or two. This rapid-fire striking behavior means that even a glancing encounter with a defensive mamba can result in multiple puncture wounds, each one delivering a fresh dose of venom. It is worth noting that the black mamba does not use its speed to chase down human beings. This is one of the most persistent myths about the animal, and it is simply not true. In the vast majority of encounters, a black mamba that detects a human approaching will attempt to flee. The snake uses its speed to escape, not to pursue. It will run, and run fast, for the nearest cover, the nearest burrow, the nearest rock crevice. The problems arise when the snake feels it cannot escape, when it is cornered in a building, surprised on a path with no clear retreat route, or when a person accidentally steps on or near it. In those situations, the flight instinct can flip to fight, and a defensive black mamba is one of the most dangerous animals you can encounter anywhere on Earth. The sensory toolkit that accompanies this speed is equally impressive. The black mamba's eyes are large for a snake, well developed, and particularly attuned to the detection of movement. A sudden gesture, a quick step, even the flicker of a camera being raised. These are the kinds of stimuli that can trigger a defensive strike. But vision is just one layer of the mamba's perceptual world. Like all snakes, the black mamba possesses a forked tongue that continuously samples its environment for chemical information. The tongue collects microscopic particles from the air and the ground, then deposits them onto the vomeronasal organ, also known as Jacobson's organ, located in a pair of small pits on the roof of the mouth. This organ processes those chemical signals with extraordinary sensitivity, allowing the mamba to build a detailed picture of what has passed through its territory, which animals are nearby, where prey has recently traveled, and whether a potential mate is in the area. Though black mambas lack external ears, they are remarkably adept at detecting vibrations transmitted through the ground. Footsteps, the movement of large animals, the rumble of an approaching vehicle, all of these produce subtle ground-borne vibrations that the mamba's lower jaw and body can pick up through its connection with the earth. The venom of the black mamba is a masterwork of biochemical engineering, a cocktail of toxins so potent and so precisely targeted that it can shut down a mammalian nervous system in minutes. Understanding how it works requires a brief detour into the molecular world, but it is a detour worth taking because the sophistication of this venom is one of the most fascinating things about the animal that produces it. In 2015, the complete protein profile of black mamba venom was characterized for the first time, revealing 41 distinct proteins and 1 nucleoside. The 2 dominant families of toxic agents are dendrotoxins and three-finger toxins, and they work together in a deadly synergy. Dendrotoxins are named after the genus Dendrospes and are unique to mamba venoms. They are small proteins, typically 57 to 60 amino acids long, cross-linked by 3 disulfide bridges. Structurally, they resemble a class of molecules called Kunitz-type protease inhibitors, but their function is entirely different. Dendrotoxins block specific subtypes of voltage-gated potassium channels in nerve cells. To understand what that means, think of your nervous system as an incredibly complex electrical circuit. Nerve signals travel along neurons as waves of electrical charge, and the flow of that charge is controlled by tiny protein gates, ion channels, embedded in the cell membranes. Potassium channels are among the most important of these gates. When a dendrotoxin plugs into a potassium channel and blocks it, the normal regulation of nerve firing goes haywire. Acetylcholine, the chemical messenger that tells muscles to contract, is released in excessive amounts. The result is involuntary muscle contractions, twitching, and, in severe cases, convulsions and paralysis. The three-finger toxins are the other major component. This family includes alpha-neurotoxins, cardiotoxins, and fasciculins, each with a different mode of attack. The alpha-neurotoxins are the most lethal. They bind to nicotinic acetylcholine receptors at the neuromuscular junction, the point where a nerve meets a muscle. By occupying these receptors, the alpha-neurotoxins prevent acetylcholine from doing its job. The muscle stops receiving the signal to contract. If this happens in the muscles that control breathing, the diaphragm and the intercostal muscles between the ribs, the result is respiratory paralysis. The victim simply stops breathing. Fasciculins, another member of the three-finger toxin family, take a different approach. They inhibit acetylcholinesterase, the enzyme that normally breaks down acetylcholine after it has done its job. With that enzyme blocked, acetylcholine accumulates at the neuromuscular junction, causing uncontrolled muscle fasciculations, the involuntary twitching that gives these toxins their name. The genius of black mamba venom lies in the way these components work together. Dendrotoxins flood the system with excess acetylcholine by forcing more of it to be released. Fasciculins prevent the breakdown of that excess acetylcholine, and alpha-neurotoxins block the receptors that acetylcholine would normally bind to. The nervous system is attacked from 3 directions simultaneously: overwhelmed, disrupted, and ultimately shut down. It is like cutting the power lines, jamming the radio signals, and destroying the control room all at the same time. In addition to these major components, black mamba venom contains smaller quantities of other biologically active molecules, including metalloproteinases, hyaluronidases, which help the venom spread through tissue, phospholipases, nerve growth factor, and a surprisingly high concentration of the nucleoside adenosine. The role of adenosine in the venom is not fully understood, but researchers have speculated that it may contribute to the rapid onset of symptoms by affecting blood flow and helping the other toxins distribute more quickly through the body. The venom also contains a peptide called calcipeptine, a 60 amino acid molecule that specifically blocks L-type calcium channels. When calcipeptine was first isolated and characterized, it was the first natural polypeptide ever discovered with this specific property. L-type calcium channels play a critical role in heart function, and their blockade contributes to the cardiovascular collapse that often accompanies severe envenomation. One of the more unusual features of black mamba venom is what it does not contain. Unlike the venoms of many other dangerous snakes, particularly vipers and some cobras, black mamba venom has very little phospholipase ATWO and virtually no protease enzymes. This means that black mamba bites typically do not cause significant local tissue damage. There is usually no dramatic swelling, no necrosis, no blackening of the flesh around the bite site. The initial symptom is often nothing more than a tingling sensation, a slight numbness around the puncture wound. This can be dangerously deceptive. A person who has been bitten by a black mamba might initially feel that the bite was not serious, that maybe they were lucky, that maybe the snake did not inject much venom. By the time the systemic symptoms begin to appear, sometimes within 10 to 15 minutes, the window for effective treatment has already begun to close. The progression of a full black mamba envenomation is swift and terrifying. Early signs include a metallic taste in the mouth, drooping eyelids, blurred vision, and difficulty swallowing. As the neurotoxins take hold, the victim may experience slurred speech, excessive salivation, nausea, abdominal pain, and sweating. Muscle twitching gives way to progressive paralysis, starting with the face and throat and moving outward to the limbs and the respiratory muscles. Without treatment, collapse can occur within 45 minutes. Death from respiratory failure typically follows within 7 to 15 hours, though in severe cases with direct vascular injection, it can come much faster. On average, a black mamba delivers somewhere between 100 and 120 milligrams of venom per bite. The lethal dose for a human being is estimated at 10 to 15 milligrams. But the snake often strikes multiple times, each strike delivering a fresh payload. In a full defensive encounter, a mamba might deliver 3, 4, even 5 bites in rapid succession. The total venom load can be staggering. The treatment is anti-venom, administered as quickly as possible. The South African polyvalent antivenom, produced by the South African vaccine producers, has been the standard treatment for decades. It is manufactured by immunizing horses with the venoms of 10 different snake species, including the black mamba, and then harvesting the antibodies from their blood serum. The antivenom is effective, but it is not without complications. Some patients experience anaphylactic reactions to the horse-derived antibodies, and the antivenom itself is expensive. A single 10 milliliter vial costs approximately $125, and a severe black mamba bite may require 6 to 15 vials. For many people in rural sub-Saharan Africa, where incomes are measured in single digits per day, this cost is simply out of reach. The lack of accessible, affordable antivenom remains one of the biggest obstacles to reducing snakebite mortality across the continent. The black mamba is a carnivore, a pure and efficient predator that feeds almost exclusively on warm-blooded prey. Its diet consists primarily of small mammals, particularly rodents like mice and rats, as well as squirrels, shrews, and, in some regions, rock hyraxes, the same plump little animals that sat in the crosshairs of our opening scene. Birds are also on the menu, especially nestlings and fledglings that cannot yet escape, and occasionally adult birds that are caught on the ground. Black mambas have been documented eating other snakes, including forest cobras, and there are anecdotal reports of large mambas consuming small antelopes. Though this is rare, the hunting strategy is elegant in its simplicity. The black mamba is an active hunter, not an ambush predator. It patrols its home range during the day, moving with its head raised, scanning for movement with its sharp eyes, and sampling the air with its forked tongue. The tongue collects airborne chemical particles and delivers them to the Jacobson's organ, a specialized chemosensory structure located in the roof of the mouth. This organ gives the snake an extraordinarily detailed picture of its chemical environment, allowing it to detect the scent trails left by potential prey from a considerable distance. When a target is identified, the mamba closes in quickly. It does not constrict its prey. It does not wrap around its victim and squeeze. Instead, it strikes, delivering 1 or 2 rapid bites, and then releases. The snake then backs off and waits. The venom does the killing. Most small mammals succumb within minutes, their nervous systems overwhelmed by the neurotoxins. Once the prey is dead, the mamba approaches and swallows it whole, head first. Powerful acids in the stomach break down the meal, bones, fur, and all, typically within 8 to 10 hours. Research in the Transvaal region of South Africa found that the mamba's recorded prey was generally quite small, mostly rodents and similarly sized mammals, as well as small birds, accounting for just 2 to 8% of the snake's own body mass. This diet of warm-blooded prey is actually one of the key factors that distinguishes the black mamba from its green mamba relatives. The other 3 mamba species, being arboreal, feed primarily on birds, lizards, and tree-dwelling frogs, a diet that is dominated by cold-blooded animals. The black mamba's shift to ground-dwelling and mammal-eating drove the evolution of its uniquely potent venom, which is optimized for quickly immobilizing fast, metabolically active prey. A mouse has a much higher metabolic rate than a lizard and can distribute venom through its body much more quickly. To be effective against such prey, the venom needs to act fast, which is exactly what black mamba venom does. The black mamba is not without enemies of its own. Several species of eagle are confirmed predators of adult mambas. Brown snake eagles are documented taking mambas up to nearly 9 feet in length. Tawny eagles and martial eagles also prey on them. For juveniles, the list of predators is longer and includes Cape file snakes, southern ground hornbills, marsh owls, hooded vultures, and Nile crocodiles, in whose stomach contents young mambas have occasionally been found. But the mamba's most famous predator is the mongoose, a small, agile mammal that has evolved a partial resistance to elapid neurotoxins. The mechanism is elegant. The mongoose's muscular nicotinic acetylcholine receptors have a slightly altered structure that prevents the snake's alpha neurotoxins from binding effectively. This does not make the mongoose completely immune to mamba venom, but it gives the animal a significant advantage in a fight. Honey badgers share a similar resistance and have also been documented killing and eating black mambas. The mating season of the black mamba spans from roughly September to February, coinciding with the warmer spring and summer months in the southern hemisphere. As temperatures rise after the cooler winter period, male black mambas begin to stir. Something shifts in their behavior. The normally solitary, home range-bound snake becomes a traveler. Males will cover considerable distances in search of females, following the faint chemical trails of pheromones that receptive females deposit in their wake. The male's forked tongue works overtime during this period, ceaselessly sampling the air and the ground for those telltale molecular signatures. When 2 or more males converge on the same female, the result is one of the most dramatic spectacles in the reptile world: plating combat. This is not a fight to the death. There are no bites, no use of venom. It is a wrestling match, a pure test of physical strength and stamina. The rival males intertwine their bodies, coiling around each other in a tight, muscular embrace. They raise the front portions of their bodies off the ground, sometimes lifting several feet into the air, and attempt to push each other down. The goal is to pin the opponent's head to the ground, demonstrating dominance. The snakes will twist, shove, and press against each other for extended periods, sometimes 15 or 20 minutes, sometimes over half an hour. The sound of their scales rubbing against each other is audible from several feet away. A dry, rasping whisper accompanied by occasional hissing, and the hollow slap of bodies hitting the ground. Observers who have witnessed this behavior describe it as mesmerizing and, honestly, a little terrifying. 2 enormous venomous snakes, each over 8 feet long, locked together in a writhing, spiraling embrace, oblivious to everything around them, completely focused on each other. South African snake catcher Nick Evans, who has witnessed mamba combat on multiple occasions, describes the males as being so absorbed in the contest that they seem entirely unaware of nearby humans. The reason the males do not bite each other during combat is a matter of some debate. One theory is that venom is a precious biological resource, energetically expensive to produce, and the snakes instinctively conserve it for hunting and self-defense. Another theory suggests that black mambas may possess some degree of resistance to their own species' venom, making biting a largely futile tactic that would not confer any competitive advantage. Whatever the reason, the result is a contest decided entirely by brute force and endurance, a demonstration of fitness that the watching female can use to evaluate the quality of her potential mate. Eventually, one male concedes, the loser uncurls, drops to the ground, and slithers away. The winner remains with the female. The actual mating process is far quieter and less dramatic than the combat that precedes it. The male approaches the female and rubs his body along hers, stimulating her through tactile contact. The female signals her receptivity by elevating her tail, allowing the male to align his cloaca, the shared reproductive and excretory opening. With hers, copulation can last for several hours. After mating, the female goes her own way. Black mambas are not pair-bonding animals. The male contributes nothing further to the reproductive process. Several weeks later, the female deposits a clutch of eggs, typically between 6 and 17, in a sheltered location. Decaying vegetation is a favored nest site because the heat generated by decomposition helps to incubate the eggs and accelerate development. Abandoned animal burrows, termite mounds, and hollow tree trunks are also used. The eggs incubate for approximately 80 to 90 days. When the hatchlings emerge, they are about 20 inches long, already equipped with venom, and completely independent. The mother does not return to the nest. There is no parental care of any kind. The baby mambas must fend for themselves from the moment they break through their eggshells. They are lighter in color than adults, typically pale gray or olive green, and they darken as they grow. Despite their small size, they are capable of catching and killing prey as large as a small rat within their first few weeks of life. Growth is rapid. A young mamba can reach 6 feet or more within its first year, but infant mortality is high. Young mambas are vulnerable to a wide range of predators, from birds of prey to mongooses to other snakes, and only a fraction of each clutch will survive to adulthood. In the wild, the lifespan of a black mamba is not well documented. The longest recorded lifespan for a captive specimen was 11 years, but wild individuals may live considerably longer. Some sources estimate that black mambas in undisturbed habitats could survive for 20 years or more, though hard data to support this is limited. What we do know is that for those individuals that survive the perilous first year, the black mamba has relatively few natural threats. Its combination of size, speed, and venom makes it a formidable animal that most predators would rather avoid. An adult black mamba in its prime, settled in a good territory with abundant prey and secure shelter, is one of the most successful and dominant predators in its ecosystem. A position earned over millions of years of evolutionary refinement. The relationship between the black mamba and the people of Africa is ancient, deep, and complicated. In dozens of cultures across the continent, the black mamba occupies a place in mythology and folklore that is reserved for only the most powerful and feared forces of nature. Among the Zulu people of South Africa, the legendary Indlandlo is a mythical, crested mamba of enormous size, said to guard mountains and rivers. Other traditions hold that the mamba has supernatural intelligence, that it can plan ambushes, that it will pursue a person for miles out of spite, that it can roll itself into a wheel and race down hillsides. None of these stories is literally true, but they speak to the profound respect and profound fear that this animal commands. In the wild, the black mamba is far more cautious and far less aggressive than its reputation suggests. Multiple experienced herpetologists and snake handlers have described the animal as shy, nervous, and strongly inclined to flee from any perceived threat. In the wild, mambas will seldom tolerate a human approaching closer than about 130 feet. At that distance, the snake will almost invariably retreat, sliding quickly into the nearest cover. The dangerous encounters happen when this escape route is blocked, when the snake is cornered in a building, trapped in a narrow space, or stepped on accidentally. In those situations, the mamba deploys its famous threat display. The front third of the body rises off the ground. The narrow neck flap, similar to a cobra's hood but less pronounced, spreads slightly. The mouth opens wide, revealing that jet black interior. The tongue flicks rapidly. The snake hisses. This is a warning. It is the mamba's way of saying, back off. If the intruder heeds the warning and slowly retreats, the snake will almost always stand down and escape. The bites happen when the warning is ignored, when the intruder moves suddenly toward the snake, or when the snake truly has no other option. A survey conducted in South Africa from 1957 to 1979 recorded over 2,500 venomous snake bites across the country, of which only 75 were confirmed as coming from black mambas. That is a tiny fraction, reflecting the fact that mambas genuinely do avoid human contact whenever possible. But those 75 bites were disproportionately serious. The black mamba is classified by the World Health Organization as a snake of the highest medical importance, a designation that reflects not the frequency of its bites, but the severity of the consequences when a bite does occur. Even with antivenom treatment, the mortality rate for confirmed black mamba envenomation has been estimated at around 14%. Without treatment, the rate historically stood at 100%. The introduction of effective antivenoms has dramatically improved survival outcomes. A mamba-specific antivenom was first developed in 1962, and a polyvalent antivenom covering multiple species followed in 1971. In the period before these treatments were available, 15 out of 35 people who received the existing, ineffective polyvalent treatment died from black mamba bites. After the mamba-specific antivenom became available, survival rates improved considerably, with most patients recovering if they reached medical care in time. The key phrase there is in time. In rural sub-Saharan Africa, where the black mamba is most commonly encountered, medical facilities are often hours away by road. Many communities lack refrigeration for storing antivenom, which has a shelf life of about 3 years and must be kept cold. Studies in Mozambique have found that as many as 59% of snakebite victims in rural areas rely on traditional medicine rather than hospital treatment. Some researchers estimate that the true death toll from snakebites across sub-Saharan Africa may be as high as 50,000 per year, many times higher than official figures suggest. Because so many cases go unreported, the appropriate response to a black mamba encounter is straightforward, though admittedly easier said than done. Do not run. Move away slowly and calmly. Do not make sudden movements. Do not attempt to kill the snake. Give the animal a wide berth and allow it to escape. If you are bitten, apply a pressure bandage to the bite site, immobilize the affected limb, and get to a hospital as quickly as humanly possible. Every minute counts, and here is where the story of the black mamba takes its most unexpected turn. Inside the same venom that can kill a human being in under an hour, scientists have discovered molecules that could one day revolutionize the treatment of chronic pain. In 2012, a team of French researchers led by Sylvie Diachat and Eric Linglia at the Institute of Molecular and Cellular Pharmacology published a groundbreaking paper in the journal Nature. They had been screening the venoms of more than 50 different snake species, looking for molecules that interact with acid-sensing ion channels, a type of protein found on the surface of pain-sensing nerve cells. When they tested black mamba venom, they found something astonishing. 2 small peptides, which they named Mambalgin 1 and Mambalgin 2, potently blocked these pain channels. When injected into laboratory mice, the Mambalgins produced pain relief as powerful as morphine. That alone would have been noteworthy. But the truly remarkable finding was what the Mambalgins did not do. Unlike morphine, which acts on opioid receptors in the brain and carries a laundry list of side effects, including respiratory depression, nausea, tolerance, and severe addiction, the Mambalgins worked through an entirely different mechanism. They targeted acid-sensing ion channels in both the peripheral nervous system and the central pain pathways, blocking pain signals without triggering the opioid system at all. In the mice, the Mambalgins did not cause respiratory depression. They did not produce tolerance nearly as quickly as morphine, and they appeared to lack the addictive potential that makes opioid painkillers so dangerous. The Mambalgins are members of the 3-finger toxin protein family, the same family that includes the deadly alpha neurotoxins in the venom. But while their closest molecular relatives are lethal, the Mambalgins themselves appear to cause no toxic effects at the doses required for pain relief. This paradox, that a substance embedded within one of the deadliest venoms on Earth could be a potent, non-addictive painkiller, captured the attention of researchers and the public alike. Pharmaceutical development based on the Mambalgins is still in its early stages. The structure has been patented, and a biotech company called the Ralpha has been working on developing Mambalgin-based compounds for human use. The road from laboratory discovery to approved medication is long and expensive, typically requiring a decade or more of toxicity testing, clinical trials, and regulatory review. But the potential is enormous. Chronic pain affects hundreds of millions of people worldwide, and the opioid crisis has demonstrated, in devastating terms, the limitations and dangers of current pain management approaches. A painkiller derived from black mamba venom that offers morphine-level relief without morphine-level risks would be a transformative medical breakthrough. And the mambalgins are not the only medically interesting molecule in the mamba's venom. Calcipeptine, the calcium channel blocker we mentioned earlier, has attracted attention from cardiovascular researchers. Dendrotoxins, for all their danger in the context of a snakebite, have become invaluable tools in neuroscience, used by researchers around the world to study the function of potassium channels in the brain. The very properties that make these molecules deadly are the same properties that make them scientifically useful. Their extraordinary specificity, their ability to target a single molecular structure with laser-like precision. There is a deep irony here, and it is one that researchers have not failed to notice. No one knows why the black mamba produces mambalgins. What possible advantage could a painkiller confer within a venom designed to kill? One hypothesis, put forward by the researchers themselves, is that the mambalgins may serve a tactical purpose during envenomation, numbing the bite site so that the prey does not immediately react, buying the venom a few extra seconds to take hold before the victim realizes it has been bitten. As for the animal itself, the black mamba is currently listed as least concern on the International Union for Conservation of Nature's Red List of Threatened Species. Its enormous range across sub-Saharan Africa, combined with the absence of any documented population decline, means that the species is not considered at risk in the near term. Black mambas are not widely traded, and there is no significant commercial exploitation of the species. They are common and widespread throughout much of their range. But the picture is not entirely rosy. Human population expansion across sub-Saharan Africa is accelerating, and with it comes habitat conversion, deforestation, and the fragmentation of wild landscapes into agricultural and residential parcels. As the human footprint grows, encounters between people and mambas will become more frequent. In many communities, the response to a mamba sighting is to kill the snake on sight, a reaction driven by understandable fear, but one that, if scaled up, could put pressure on local populations. A study published in Conservation Letters has called for immediate policy action targeting human perceptions of snakes, arguing that fear-based killing of snakes is not only unnecessary, but ecologically harmful. Black mambas play an important role in their ecosystems, primarily through the regulation of rodent populations. Rodents are agricultural pests and carriers of diseases that affect both humans and livestock. A healthy population of mambas is, in a very real sense, a form of natural pest control. The future of the black mamba, like the future of so much of Africa's wildlife, will depend on whether humans can find a way to coexist with an animal that frightens them. It will depend on the availability of affordable antivenom, on education about snakebite prevention and first aid, and on the preservation of the wild habitats that the mamba calls home. It will depend, ultimately on whether we can look past the fear and the mythology and see the black mamba for what it truly is. Not a monster, not a villain, but an ancient and magnificent predator, a masterpiece of evolution that has been perfecting its craft for millions of years. Long before we ever showed up, there is a moment, if you are lucky enough to see a black mamba in the wild, and if you are at a safe distance, when the fear fades just enough for wonder to take its place. The animal is startlingly beautiful. The way it moves is fluid, fast, and purposeful. The way it raises its head, alert, aware, scanning the landscape with those dark, intelligent eyes. The way the light catches its scales, turning that gunmetal gray into something almost luminous. In that moment, you understand why this snake has haunted the imagination of a continent. And you understand, too, that the world would be a lesser place without it. Sleep well tonight, and if you dream of Africa, dream of the savanna, the rocky outcrops, the warm sun on dry earth, and a long, dark shape moving through the grass, ancient and unhurried, carrying death in its fangs and miracles in its blood.